uncover the hidden legacy of the ancient world. From the wheel to medical marvels, the innovations of our ancestors are still powering our modern lives. Join us on Ancient Odyssey as we count down the top 46 game-changing inventions that transform civilizations and continue to shape our future. Get ready to discover the surprising origins of tools, systems, and ideas that drive humanity forward. Watch until the end to see how the past is still shaping our world today. Number 46. Wheel and axle. The wheel and axle are one of humanity's most transformative inventions, revolutionizing transport, engineering, and technology. Archaeological evidence places its earliest known use around 3,500 BCE in Mesopotamia, particularly in the Sumerian city-states. The earliest wheels were solid wooden discs carved from planks and mounted on a fixed axle, primarily used for pottery making before being adapted for transportation. The combination of wheel and axle created a system that reduced friction and allowed heavier loads to be moved with far less effort, enabling the rise of carts and wagons. This innovation accelerated trade, expanded agriculture, and even influenced warfare, as chariots became a dominant force in ancient military tactics. The wheel's concept spread rapidly, appearing in the Indus Valley Civilization, ancient China, and Europe within centuries. Over millennia, the design evolved into spoked wheels, improving speed and efficiency. Today, the wheel and axle principle remains a cornerstone of modern engineering. It is visible not only in vehicles such as cars, trucks, and trains, but also in countless machines, such as gears, pulleys, and turbines, which all rely on the same basic mechanics first harnessed thousands of years ago. Whether in high-speed transportation systems or everyday devices like rolling suitcases and bicycles, the wheel and axle continue to turn the gears of civilization, proving that an idea from ancient Mesopotamia still drives the modern world. Number 45. Plough. The plough, specifically the ard or scratch plough, is one of the earliest agricultural tools that transformed human civilization by enabling large-scale farming. Its invention dates back to around 400 to 3500 BCE in the ancient Near East, with early evidence found in Mesopotamia and the Indus Valley Civilization. The ard consisted of a simple wooden frame with a pointed tip that was dragged through the soil by human or animal power, breaking the ground surface to prepare it for planting. Unlike later plows with moldboards, the ard did not turn the soil but scratched furrows into it, making it most effective in light, sandy, or silty soils. This innovation allowed ancient farmers to cultivate larger areas more efficiently than with hand tools, leading to increased food production, population growth, and the rise of complex societies. The plow's spread was rapid, reaching ancient Egypt, Europe, and China within centuries, with local variations adapted to different terrains. Today, the basic principle of the ard remains at the heart of modern agricultural machinery. While contemporary plows are made of metal and powered by tractors, they still function to break and prepare soil for planting, an essential step in crop cultivation. In some parts of the world, traditional wooden ards pulled by oxen or donkeys are still in use, proving that this 6,000-year-old innovation continues to sustain human life in both traditional and mechanized forms. Number 44. Irrigation systems. Irrigation systems, particularly canals and basin irrigation, were among the most vital innovations of the ancient world, enabling civilizations to thrive in regions with seasonal or unpredictable rainfall. The earliest large-scale irrigation networks date back to around 6000 BCE in ancient Mesopotamia, where Sumerian engineers constructed canals and levees to divert water from the Tigris and Euphrates rivers onto farmlands. By 3000 BCE, ancient Egyptians had developed an advanced basin irrigation system, using the predictable flooding of the Nile to fill large, enclosed fields, which would retain water long enough to nourish crops before draining. This allowed consistent agricultural yields, even in arid climates, and supported the growth of cities, trade, and centralized states. Similar systems emerged independently in the Indus Valley and ancient China, where large canals and dikes regulated water for rice and other crops. The principles of these early irrigation methods still underpin modern agriculture. Today's large-scale irrigation infrastructure, whether massive canal networks in countries like India and Pakistan or controlled flooding systems in rice-producing regions, uses the same fundamental idea of directing and managing water flow to sustain crops. Modern technologies such as dams, pumps, and automated gates have improved efficiency, but in many rural areas worldwide, farmers still employ simplified versions of ancient canal or basin irrigation. This enduring technology continues to be a lifeline for agriculture, demonstrating how innovations from Mesopotamia and the Nile Valley still feed millions in the 21st century. Number 43. Sail and ancient shipbuilding. The sail and ancient shipbuilding innovations such as the keel, hull, and steering oar were pivotal in transforming human transportation and trade. The earliest known sailing vessels date back to around 3500 BCE in ancient Egypt, where reed boats equipped with square sails harnessed the wind to navigate the Nile. By 3000 BCE, the Mesopotamians were also using sail-powered boats for river and coastal trade in the Persian Gulf. The introduction of the keel, a central structural beam running along the bottom of the ship, by ancient seafarers such as the Phoenicians improved stability and seaworthiness, allowing for longer voyages. Hull designs evolved from simple dugouts to planked wooden constructions, enabling larger cargo capacities. The steering oar, used in Egypt and later perfected by the Greeks and Romans, provided greater control over direction, especially in open waters. These innovations expanded maritime trade networks, connected distant cultures, and facilitated exploration. Today, the principles developed in ancient shipbuilding still shape modern naval architecture. The keel remains a critical structural element in ships and yachts. Hull designs are optimized using the same basic concepts, and the steering oar's function survives in the form of rudders. Modern sailing vessels, from small yachts to tall ships, still employ sails that operate on the same aerodynamic principles used thousands of years ago. Even advanced cargo ships and naval vessels rely on the structural ideas pioneered in antiquity, proving that the ingenuity of early shipbuilders continues to guide maritime technology today. Number 42. Aqueducts and gravity-fed water supply. Aqueducts and gravity-fed water supply systems stand as one of the most impressive feats of ancient engineering, delivering fresh water over long distances without pumps. While early forms of channeling water existed in Mesopotamia and Egypt, the most advanced examples emerged in the ancient Roman world from around the 4th century BCE. Roman engineers perfected the use of stone, brick, and concrete channels, precisely graded to allow water to flow steadily from springs or rivers to cities, baths, fountains, and agricultural lands. Some aqueducts stretched for tens of kilometers, incorporating tunnels, bridges, and monumental arches to cross valleys. The use of settling tanks ensured cleaner water, and the system operated solely through gravity, relying on meticulous surveying and construction techniques. This technology enabled large urban populations to thrive and supported public sanitation on an unprecedented scale. The principle of gravity-fed water delivery is still in use today. Modern municipal water systems often draw from reservoirs at higher elevations, allowing gravity to move water through pipelines to treatment plants and homes, reducing reliance on mechanical pumping. In rural and mountainous areas, gravity-fed irrigation systems still channel water to fields much as they did in antiquity. Even in contemporary civil engineering, the Roman mastery of gradient, durability, and efficient flow continues to inspire water infrastructure design, proving that their ancient aqueducts were more than monuments. They were practical systems that set the standard for sustainable water supply. Number 41. Arch, vault, and dome architecture. The development of the arch, vault, and dome in architecture marked a turning point in the history of construction, allowing builders to create larger, stronger, and more enduring structures. The true arch was first used extensively by the ancient Mesopotamians around the 2nd millennium BCE, but it was the Romans, from the 3rd century BCE onward, who perfected and combined the arch with the barrel vault and the dome to create monumental and functional buildings. The arch's curved form distributes weight evenly, enabling the construction of bridges, aqueducts, and gateways that could span greater distances than post and lintel designs. By extending the arch, Roman engineers created the barrel vault, allowing for vast roofed spaces without interior supports. The dome, exemplified in the Pantheon in Rome, completed in 126 CE, represented the pinnacle of this architectural evolution, enclosing massive spaces with elegance and stability. These innovations revolutionized public architecture, from baths and amphitheaters to temples and basilicas. Today, the principles behind the arch, vault, and dome remain fundamental in architecture and engineering. Modern bridges, stadiums, cathedrals, and government buildings still employ arches for strength and aesthetics, vaults for expansive interiors, and domes for iconic skylines. Advances in steel and reinforced concrete have allowed these ancient forms to be built on an even grander scale, but the core ideas remain the same, proving that concepts first mastered by ancient civilizations continue to shape the structures of the modern world. Number 40. Roman concrete. Roman concrete, known as pozzolanic concrete, was a groundbreaking building material that allowed the ancient Romans to construct structures of unparalleled durability. Developed around the 3rd century BCE, this material was first used extensively in the Roman Republic and Empire, with early examples found in harbors, aqueducts, and monumental buildings. Its key ingredient was volcanic ash, particularly from the area around Pozzuoli in Italy, which, when mixed with lime and water, produced a chemical reaction that created a remarkably strong and water-resistant binder. Unlike modern Portland cement, Roman concrete could set underwater, making it ideal for harbor and bridge construction. This innovation enabled architectural feats such as the Colosseum, the Aqueducts, and the Pantheon, whose massive unreinforced concrete dome still stands today. The secret of Roman concrete lay in its durability. Many ancient structures remain intact after over 2 millennia, resisting environmental erosion far better than many modern concretes. Today, the basic principles of pozzolanic concrete are still in use. Modern engineers incorporate volcanic ash or similar materials, like fly ash, to improve the strength, durability, and sustainability of concrete. These mixes are especially valuable in marine construction, echoing the Roman mastery of underwater building. By combining local natural materials with innovative chemistry, Roman builders created a legacy that continues to influence construction technology, proving that their ancient formula was not only an engineering triumph, but also a model for modern sustainable building practices. Number 39. Road building techniques. Ancient road building techniques, particularly paved roads, were perfected by the Romans and became a defining feature of their engineering legacy. While earlier civilizations such as the Mesopotamians and Minoans constructed stone-paved streets as early as 2000 BCE, it was during the Roman Republic and Empire, beginning around the 3rd century BCE, that road construction reached unprecedented sophistication. Roman engineers built roads in multiple carefully layered sections: a foundation of large stones, a middle layer of gravel or crushed rock, and a top surface of tightly fitted stone slabs. These roads were slightly convex to allow rainwater to drain to the sides, with ditches running parallel for further drainage. Designed for durability and efficiency, the Roman road network eventually stretched over 400,000 kilometers, linking cities, forts, and ports across Europe, North Africa, and the Middle East. This infrastructure enabled rapid military movement, facilitated trade, and unified far-flung provinces. Many Roman roads remained in use for centuries after the empire's fall, forming the basis of modern European transport routes. Today's road construction still follows the Roman principle of layered foundations for stability and drainage, though asphalt and concrete have replaced stone paving. In rural and historic areas, some original Roman roads remain intact and passable, a testament to the enduring genius of their design. The core concepts of strong foundations, proper grading, and effective drainage continue to guide modern highway engineering, proving that the Roman approach to road building still shapes how we travel today. Number 38. Sewers and urban sanitation systems. Sewers and urban sanitation systems were among the most crucial public health innovations of the ancient world, enabling dense populations to thrive by managing waste and preventing disease. One of the earliest known examples comes from the Indus Valley Civilization around 2600 BCE, where cities like Mohenjo-Daro featured covered brick drains running along streets, connected to household bathing areas and latrines. In ancient Rome, large-scale sewer systems such as the Cloaca Maxima, constructed beginning in the 6th century BCE, carried wastewater from public baths, fountains, and latrines into the Tiber River. Built with stone and later reinforced with Roman concrete, these sewers not only removed waste, but also drained stormwater, reducing flooding in urban areas. Other ancient cultures, including the Minoans of Crete and the Mesopotamians, developed sophisticated drainage channels and cesspits, showing that sanitation was a shared priority across early civilizations. The fundamental principles behind these ancient systems are still applied today, specifically channeling wastewater away from living areas and ensuring proper drainage. Modern urban sanitation networks rely on underground sewers, treatment plants, and storm drains, but their purpose remains identical: protecting public health and maintaining hygiene. In some historic cities, parts of ancient sewer systems remain in use or serve as the foundation for modern infrastructure. This continuity reflects the enduring importance of sanitation engineering, proving that the solutions devised thousands of years ago still underpin the functioning of healthy, sustainable cities worldwide. Number 37. Hypocaust. The hypocaust was an ingenious ancient heating system that provided underfloor and central heating to buildings, particularly public baths and wealthy homes. Developed by the Romans around the 1st century BCE, the system worked by circulating hot air from a furnace through a network of empty spaces beneath the floor and within hollow wall flues. Floors were supported on small pillars called pili, creating a cavity into which heated air and smoke could flow, warming the floor above and radiating heat into the room. This innovation created a comfortable indoor environment, especially in colder parts of the Roman Empire such as Britain and Gaul, and was a key feature of Roman bathhouses, where maintaining warm air and water temperatures was essential. The hypocaust was a significant step toward climate control in architecture, influencing later heating technologies in the Byzantine and Islamic worlds. While the original system required constant manual operation and a steady fuel supply, its core principle, radiant heat from beneath the floor, survives in modern underfloor heating systems. Today, electric or water-based radiant floor heating uses similar concepts to evenly distribute warmth in homes and commercial buildings. The hypocaust also foreshadowed central heating systems that circulate heated air or water throughout a structure. This continuity shows that an idea first realized in ancient Rome remains a valued comfort technology, blending efficiency with luxury in much the same way it did over 2,000 years ago. Number 36. Archimedes Screw. The Archimedes Screw, also known as the screw pump, is a simple yet brilliant device for raising water from a lower level to a higher one. It is traditionally attributed to the ancient Greek mathematician and inventor Archimedes, who is said to have devised it around the 3rd century BCE in the city of Syracuse. Consisting of a helical surface contained within a cylinder or an open trough, the device is operated by rotating the screw, either by hand or with the help of animals, to lift water along its spiral path. While Archimedes may have refined or popularized it, similar devices may have existed earlier in Egypt for irrigation, particularly to lift Nile water into agricultural canals. The screw pump proved invaluable for irrigation, draining flooded lands, and supplying water to cities and ships. Its efficiency and simplicity ensured that it spread widely across the ancient Mediterranean and beyond. Today, the Archimedes screw remains in use in various forms. It is still employed in rural and developing regions for irrigation and drainage, often powered by hand or small motors. In modern engineering, the same principle is used in large-scale water management systems, including wastewater treatment plants, and even in micro-hydroelectric systems where the screw operates in reverse to generate power from flowing water. Its enduring relevance over more than 2 millennia is a testament to the ingenuity of ancient engineering and the timeless utility of well-designed mechanical solutions. Number 35. Water wheels and water mills. Water wheels and water mills were transformative ancient technologies that harnessed the power of flowing water to perform mechanical work. The earliest evidence of water wheels dates to around the 3rd century BCE in the Hellenistic world, with Greek engineers developing vertical wheel designs to lift water for irrigation. By the 1st century BCE, the Romans had adapted the concept to power mills for grinding grain, as described by the engineer Vitruvius. These early mills used the force of rivers or aqueduct-fed channels to turn a wheel connected to millstones, greatly increasing the speed and efficiency of grain processing compared to manual labor. Some Roman complexes, such as the massive Barbegal mill in southern France, could process enough flour to feed entire cities. Variations of the water wheel soon spread to China, the Middle East, and Europe, where they powered hammers, sawmills, and textile machinery. Today, the fundamental principle of converting water's kinetic energy into mechanical energy is still applied. Traditional water mills remain in use in parts of the world for grinding grain or generating small-scale power. In modern times, the concept has evolved into hydroelectric power plants, where turbines, essentially advanced water wheels, generate electricity on a massive scale. From ancient irrigation and food production to renewable energy, The Waterwheels' enduring role demonstrates how an ancient innovation continues to drive human progress. Number 34. Simple machines. Simple machines such as the pulley, lever, and screw are foundational mechanical devices that have been used since antiquity to make work easier by amplifying force. The lever is the oldest of the three, with evidence of its use as early as 5000 BCE in the ancient Near East and Egypt, where it likely appeared in the form of shadufs, which are long poles with counterweights used to lift water for irrigation. The pulley emerged later, with written accounts from the 7th to 6th centuries BCE in Mesopotamia and Greece. Greek engineer Archimedes famously demonstrated compound pulley systems in the 3rd century BCE to lift heavy loads with minimal effort. The screw, as a simple machine, is credited to Archimedes in the same era, primarily for raising water, though threaded fasteners and pressing screws developed later in the ancient Mediterranean. These devices were indispensable in construction, transport, and agriculture, enabling ancient civilizations to build monumental architecture, move massive stones, and irrigate fields efficiently. Today, the principles of the pulley, lever, and screw are embedded in countless tools and machines. Levers operate in everything from crowbars to scissors. Pulleys are essential in cranes and elevators, and screws are ubiquitous in fastening systems and mechanical assemblies. The fact that these ancient inventions remain integral to modern engineering highlights their timeless efficiency and the ingenuity of early innovators who discovered how to harness basic physical principles to accomplish extraordinary feats. Number 33. Bronze metallurgy. Bronze metallurgy, involving the smelting and casting of copper and tin to create a stronger alloy, marked one of the most significant technological leaps in human history. This innovation emerged during the late 4th millennium BCE, with early evidence from Mesopotamia, Anatolia, and the Iranian plateau. By around 3300 BCE, the practice had spread widely, giving rise to what historians call the Bronze Age. Bronze was far harder and more durable than pure copper, allowing ancient craftsmen to produce superior weapons, tools, armor, and ceremonial objects. The process began with the extraction and smelting of copper and tin ores at high temperatures, followed by carefully combining them in furnaces to create molten bronze. The liquid metal was then poured into clay or stone molds to form finished items, a technique known as casting. This new material revolutionized agriculture through stronger plowshares and sickles, transformed warfare with sharper swords and spearheads, and enhanced art with intricate statues and decorative items. Although iron eventually supplanted bronze for many practical uses, bronze casting remains important today. It is still employed for sculptures, musical instruments, bearings, and components requiring corrosion resistance. Modern foundries use advanced furnaces, but the principles of alloying metals and pouring them into molds remain essentially the same as those mastered over 5,000 years ago. Bronze metallurgy not only shaped the ancient world, but also laid the foundation for the metalworking traditions that still drive human industry. Number 32. Iron smelting and forging. Iron smelting and forging represented a major technological advance that reshaped ancient economies, warfare, and daily life. The earliest evidence of iron smelting appears around 1500 BCE in Anatolia, modern-day Turkey, where the Hittites are believed to have developed techniques for extracting iron from ore using high-temperature furnaces. Unlike copper and bronze, iron ore is abundant, making the metal more widely available once the technology spread to the Near East, India, China, and Africa. By heating iron ore with charcoal in a bloomery, ancient smiths produced a spongy mass of metallic iron, which was then hammered to remove impurities in a process called forging. This produced stronger and more durable tools, weapons, and agricultural implements. In South India, by around 300 BCE, metallurgists developed wood steel, an exceptionally high-quality crucible steel renowned for its sharpness and resilience, later inspiring the famed Damascus steel of the medieval period. Iron strength transformed ancient societies, enabling more efficient farming, more effective weapons, and monumental construction. Today, the principles of iron smelting and forging remain at the heart of modern metallurgy. While blast furnaces, electric arc furnaces, and advanced alloys have replaced ancient methods, blacksmithing traditions survive, and high-carbon specialty steels still owe much to ancient innovations like woods. From skyscrapers to surgical tools, the modern world continues to rely on the mastery of iron first achieved thousands of years ago. Number 31. Glassmaking. Glassmaking is one of humanity's earliest and most versatile crafts, with origins tracing back to around 2500 BCE in Mesopotamia and ancient Egypt. Early glass was not transparent, but opaque or translucent, produced by melting silica with plant ash and lime, then shaping it into beads, amulets, and small vessels through casting and core-forming techniques. Over centuries, glassmaking spread across the ancient world, with artisans in the Levant refining the process. A revolutionary leap came around the 1st century BCE in the Roman-controlled region of Syria, where craftsmen invented glassblowing. By using a hollow tube to inflate molten glass, artisans could create thinner, larger, and more intricate vessels quickly and efficiently. This innovation made glass more affordable and widespread, transforming it from a luxury material into a common household commodity. The Romans further improved transparency and clarity, enabling the production of windows, decorative items, and tableware. Today, glassmaking remains a cornerstone of modern industry, still relying on the same basic principles developed in antiquity: melting silica with additives and shaping it while hot. Glassblowing survives both as an artisanal craft and an industrial process, producing everything from art pieces to laboratory equipment. The ancient skill that once adorned pharaohs' tombs and Roman banquet tables now finds its place in skyscraper windows, smartphone screens, and fiber optic cables, proving the enduring legacy of glass in human civilization. Number 30. Papermaking. Papermaking was first developed during the Eastern Han Dynasty in China, traditionally credited to the court official Cai Luan around 105 CE. Before this breakthrough, people in China wrote on bamboo slips, silk, or wooden tablets, which were either cumbersome or expensive. Cai Luan's innovation involved pulping plant fibers, such as mulberry bark, hemp, rags, and old fishing nets, mixing them with water, pressing the mixture into thin sheets, and drying them. This created a lightweight, portable, and affordable writing surface that revolutionized the recording and dissemination of information. Initially reserved for official documents and scholarly works, paper quickly became essential for education, administration, and the spread of literature. From China, papermaking technology spread along trade routes to the Islamic world by the 8th century and into Europe by the 11th and 12th centuries, fueling advances in science, art, and governance. The invention was a cornerstone of human knowledge sharing, paving the way for the later invention of printing. In the modern world, papermaking still follows the same fundamental principle of creating sheets from pulp, though it now uses industrial machinery and incorporates wood pulp as the primary material. While digital media has reduced paper demand in some areas, it remains indispensable for books, packaging, currency, and countless everyday uses. The Han-era innovation continues to shape how humanity records, communicates, and preserves its ideas more than 1,900 years after its creation. Number 29. Writing systems and alphabets. The Phoenician writing system, developed around 1050 BCE in the ancient Levant, is considered one of the most influential innovations in human history. Unlike earlier complex scripts, such as Egyptian hieroglyphs or Mesopotamian cuneiform, which used hundreds of symbols, the Phoenician script consisted of only 22 characters representing consonant sounds. This phonetic approach made reading and writing more accessible, especially for merchants engaged in long-distance trade across the Mediterranean. As the Phoenicians established colonies and trading posts, their alphabet spread to cultures such as the Greeks, who adapted it around the 8th century BCE by adding vowels, creating the first true alphabet. This Greek system later evolved into the Latin alphabet used by the Romans, whose empire carried it across Europe and beyond. Today, the Latin alphabet, directly descended from this Phoenician Greek lineage, is the most widely used writing system in the world, forming the basis for English, Spanish, French, and many other languages. Its simplicity and adaptability have allowed it to endure for over 3 millennia, shaping literature, law, science, and communication across civilizations. From ancient inscriptions carved in stone to the digital text on modern screens, the legacy of the Phoenician alphabet continues to serve as a foundation for human expression and record-keeping, linking today's global communication systems to their roots in the ancient Mediterranean world. Number 28. Place-value decimal numeral system. The place-value decimal numeral system, including the crucial concept of zero as a numeral, was developed in ancient India between the 1st and 6th centuries CE. Earlier civilizations, such as the Babylonians and Mayans, had place-value systems, but it was Indian mathematicians who refined it into the fully functional decimal system we use today. In this system, the position of a digit determines its value, units, tens, hundreds, and so on, and the inclusion of zero allowed for representing large numbers and performing complex calculations with unprecedented efficiency. The earliest recorded use of a symbol for zero appears in inscriptions from the 5th century CE, with scholars like Aryabhata and Brahmagupta formalizing its mathematical properties. From India, this system spread to the Islamic world through trade and scholarship around the 8th century, where it was further studied and transmitted to medieval Europe via Arabic texts. Hence the term Arabic numerals, though their roots are Indian. Today, the decimal numeral system is the global standard for mathematics, science, commerce, and digital technology. Whether in balancing a budget, programming a computer, or sending a spacecraft to Mars, the same core principles devised in ancient India remain at work. This innovation transformed mathematics from a cumbersome, limited tool into a universal language, making it one of the most important intellectual achievements in human history. Number 27. Euclidean geometry and Pythagorean theorem. Euclidean geometry and the Pythagorean theorem stand as two foundational pillars of ancient mathematics, developed in ancient Greece between the 6th and 3rd centuries BCE. The Pythagorean theorem, attributed to the mathematician and philosopher Pythagoras around the 6th century BCE, states that in a right-angled triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. While knowledge of this relationship existed in earlier civilizations such as Babylon and Egypt, it was in Greece that it was rigorously proven and integrated into a broader mathematical framework. Centuries later, Euclid of Alexandria compiled the Elements around 300 BCE, systematically presenting the principles of geometry into a logical, axiomatic system. Euclid's work not only incorporated the Pythagorean theorem, but also defined the very way geometry was taught for over 2 millennia. These principles allowed ancient engineers, architects, and astronomers to design temples, map the stars, and calculate land divisions with remarkable precision. Today, Euclidean geometry and the Pythagorean theorem are still fundamental in education, architecture, engineering, navigation, computer graphics, and even modern space exploration. From constructing bridges to programming virtual 3D environments, the logical framework laid down in ancient Greece continues to guide problem-solving across countless fields. These discoveries embody the enduring power of clear reasoning and mathematical proof, bridging over 2,000 years of human intellectual progress. Number 26. Trigonometry. Trigonometry, the branch of mathematics dealing with the relationships between angles and sides of triangles, traces its origins to the Hellenistic period, particularly between the 3rd and 2nd centuries BCE in ancient Greece. Its development was closely tied to astronomy, as Greek mathematicians sought precise methods to calculate celestial movements. Hipparchus of Nicaea, often called the father of trigonometry, compiled the first known trigonometric table around 150 BCE, using chords of a circle to relate angles to distances. His work built on earlier Babylonian and Egyptian measurements, but formalized them into a systematic mathematical discipline. Claudius Ptolemy later expanded on these ideas in his Almagest, 2nd century CE, providing detailed trigonometric methods for predicting planetary positions. Trigonometry allowed ancient astronomers to determine distances to celestial bodies, navigate seas with greater accuracy, and refine calendar systems. Today, trigonometry is indispensable in a vast range of fields, from engineering, architecture, and surveying to physics, GPS technology, and computer graphics. It underpins satellite communication, enables 3D modeling in video games, and supports navigation systems that guide ships and aircraft across the globe. What began as a tool for mapping the heavens in the Hellenistic world has become a universal mathematical language, essential for both exploring the cosmos and designing the technologies of modern life. Number 25. Surgical instruments and operative techniques. Ancient surgical instruments and operative techniques reflect the remarkable medical knowledge of early civilizations, particularly in ancient India, Greece, and Rome. Around the 6th century BCE, the Indian physician Sushruta, often called the father of surgery, described over 120 surgical instruments in his medical text, the Sushruta Samhita. These tools, crafted from metal, included scalpels, forceps, needles, and probes, many of which closely resemble modern surgical implements. Sushruta detailed complex procedures such as cataract removal, rhinoplasty, and wound suturing, emphasizing cleanliness and precision. In the Greco-Roman world, physicians like Hippocrates and Galen advanced surgical theory and practice between the 5th century BCE and the 2nd century CE. Roman surgeons used bronze and iron instruments, performing operations for battlefield injuries, setting broken bones, and removing bladder stones. Surgical kits recovered from archaeological sites in Pompeii and other Roman towns reveal highly specialized tools such as bone drills, cautery devices, and speculums. These ancient innovations laid the foundation for modern surgery. While materials and sterilization methods have greatly advanced, many instrument designs, like scalpels, retractors, and forceps, retain the same basic shapes envisioned over 2 millennia ago. Operative techniques developed by pioneers such as Sushruta and Greco-Roman surgeons continue to influence modern medical procedures, proving that the quest to heal through precise and skillful intervention is a legacy stretching from the ancient operating table to today's advanced surgical theaters. Number 24. Brewing and Fermentation. Brewing and fermentation are among humanity's oldest biochemical discoveries, dating back to at least 5,000 to 4,000 BCE in ancient Mesopotamia and Egypt. Archaeological evidence from Sumerian sites reveals clay vessels containing residues of fermented barley, indicating the production of early beer. The Sumerians even composed hymns to Ninkasi, the goddess of beer, celebrating the drink's cultural and social importance. Around the same period, the ancient Egyptians refined brewing methods, producing a range of beers that were staples in their diet and a form of payment for workers. Fermentation was also applied to bread making, with the Egyptians credited around 3000 BCE for developing leavened bread. They discovered that dough left to rest could rise naturally due to wild yeast and bacteria in the environment. This process produced softer, airier bread compared to earlier flatbreads, marking a significant culinary advancement. Both beer brewing and bread leavening rely on the same fundamental biochemical reaction. Microorganisms, mainly yeast, convert sugars into alcohol and carbon dioxide. While the alcohol defines beer, the carbon dioxide gives bread its fluffy texture. Today, brewing and baking have evolved into global industries, yet the underlying processes remain virtually unchanged from their ancient origins. Modern breweries still use barley, yeast, and water, just with more controlled techniques, while bakeries worldwide depend on yeast fermentation for countless bread varieties. From craft beers to artisan loaves, these ancient innovations continue to shape cultural traditions, social gatherings, and daily diets around the world. Number 23. Textile weaving and the loom. Textile weaving, using the warp and weft technique, is one of humanity's oldest crafts, with origins tracing back to at least 6000 BCE in ancient Mesopotamia and the Nile Valley. Early weavers used simple frame looms to interlace vertical threads or warp, with horizontal threads or weft, creating fabrics for clothing, household use, and trade. By around 4000 BCE, the Egyptians had developed more advanced vertical looms, enabling the production of finer, more durable linen that was highly prized across the ancient world. In ancient China, weaving technology flourished during the Shang dynasty between 1600 to 1046 BCE, particularly in silk production, which relied on the same warp and weft principle but with delicate silk threads. The Greeks and Romans also advanced loom design, introducing devices like the warp-weighted loom to improve tension control and pattern complexity. The warp and weft system became a global standard because of its versatility, allowing countless patterns, textures, and materials to be produced. Over time, weaving moved from household craft to large-scale production, with looms central to textile economies. Today, the fundamental concept remains unchanged. Modern industrial looms, often computer-controlled, still interlace warp and weft threads to create fabrics ranging from cotton denim to high-tech synthetic blends. The ancient technology not only survives but thrives, forming the backbone of the global textile industry. From traditional hand-woven rugs to precision-engineered fabrics for aerospace use, the warp and weft method is a direct legacy of humanity's earliest weavers. Number 22. Sundials and water clocks. Sundials and water clocks were among the earliest methods humans devised to measure time, long before mechanical clocks existed. The sundial, which uses the shadow cast by a fixed object known as a gnomon to indicate the time of day, dates back to at least 1500 BCE in ancient Egypt, where tall obelisks and portable stone dials helped track daylight hours. The concept spread to Greece and Rome, where more sophisticated designs accounted for seasonal changes in the sun's path. Water clocks, or clepsydras, emerged around the same period, with early examples found in ancient Babylon and Egypt. These devices measured time by the regulated flow of water from or into a container. The Greeks refined the clepsydra by adding markings and gears for greater accuracy, while in ancient China, elaborate water clocks powered by dripping mechanisms and rotating figures became both practical tools and works of art. Both sundials and water clocks transformed daily life in the ancient world, enabling more precise scheduling for agriculture, religious rituals, legal proceedings, and navigation. They also laid the groundwork for the scientific study of astronomy and time measurement. Although modern society relies on mechanical, quartz, and atomic clocks, sundials still serve decorative and educational purposes in gardens and public spaces, and water clocks are recreated in museums and science exhibits. Their core principles, tracking time through celestial movement and steady fluid flow, remain a testament to the ingenuity of early civilizations in mastering the passage of time. Number 21. Calendar systems. The development of calendar systems was a vital achievement in the ancient world, allowing civilizations to organize agricultural cycles, religious festivals, and civic life. One of the earliest and most influential was the Egyptian calendar, developed around 3000 BCE. Based on the annual flooding of the Nile and the heliacal rising of the star Sirius, it used a 365-day year divided into 12 months of 30 days, plus 5 extra days for festivals. This solar-based system was remarkably accurate for its time and influenced later Mediterranean timekeeping. Centuries later, the Roman world adopted the Julian calendar, introduced by Julius Caesar in 45 BCE. Drawing from Egyptian solar principles and Greek astronomical knowledge, it set a year at 365 days with an extra leap day every 4 years to better align with Earth's orbit. This reform eliminated the confusion caused by Rome's earlier lunar calendar, which had been subject to political manipulation. These ancient systems shaped how societies perceived and managed time, linking civic order to astronomical observation. The Julian calendar was used across Europe for over 1,600 years until refined into the Gregorian calendar in 1582, which remains the international standard today. Modern calendars, whether for religious observance or civil administration, still echo these ancient innovations. The division of the year into months, the leap year system, and solar alignment are direct inheritances from the Egyptian and Julian systems, reflecting the enduring legacy of early timekeeping mastery. Number 20. Soap and early cleansing compounds. The origins of soap and cleansing compounds can be traced back to ancient Mesopotamia around 2800 BCE, where Babylonian tablets record recipes for a substance made from water, alkali, and cassia oil. This early form of soap was likely used for cleaning textiles rather than personal hygiene. By 1550 BCE, the ancient Egyptians had developed a similar product by combining animal or vegetable oils with alkaline salts, which they used for both washing and treating skin ailments. The practice spread to the Greco-Roman world, where cleansing rituals often involved scraping the skin with a strigil after applying oil, though evidence shows that soaps made from tallow and ashes were also produced. In ancient Rome, Pliny the Elder described soap as an invention of the Gauls, noting its use both for cleaning and as a hair treatment. These early formulations relied on a simple chemical reaction, saponification, between fats and alkaline substances, a principle still used in soap making today. Modern soap, while often refined with fragrances, moisturizers, and synthetic detergents, is still fundamentally based on the same ancient process. From bars and liquid soaps to specialized antiseptic and skincare products, the idea of combining fats or oils with alkalis for cleansing remains unchanged. What began as a practical solution in ancient civilizations has evolved into an essential element of daily hygiene worldwide, proving that some of humanity's oldest innovations never truly wash away. Number 19. Lenses and basic optics. The study and use of lenses and basic optics can be traced back to the ancient world, with some of the earliest known examples dating to around 700 BCE in Mesopotamia. The famous Nimrud lens, discovered in Assyria, is a polished rock crystal that may have been used as a magnifying glass or for concentrating sunlight. The ancient Egyptians and Greeks also experimented with polished quartz and glass to bend and focus light. By the 5th century BCE, Greek philosophers like Empedocles and later Euclid and Ptolemy began studying the principles of vision, reflection, and refraction, laying the theoretical groundwork for optics. In the Islamic Golden Age between 8th to 13th century CE, scholars such as Alhazen made groundbreaking contributions to optical science, correctly explaining that vision occurs when light reflects off objects into the eye. These developments in both theory and practice set the stage for precision lenses in the medieval and Renaissance periods. Today, the same basic optical principles discovered in antiquity are used in countless technologies, from eyeglasses and microscopes to cameras, telescopes, and laser systems. Modern lenses, whether made from glass or advanced polymers, rely on carefully engineered curvature and refractive properties to bend light in predictable ways. The ancient world's curiosity about light not only improved vision, but also illuminated pathways for modern science, proving that a simple polished stone could one day lead to space telescopes exploring the farthest reaches of the universe. Number 18. Odometer. The odometer, a device for measuring distance traveled, has its origins in the ancient world, with evidence suggesting it was developed independently in several cultures. The earliest known descriptions come from ancient Greece in the 3rd century BCE, attributed to Archimedes and later improved by Hero of Alexandria in the 1st century CE. The Romans, by the time of Vitruvius, also 1st century BCE, had incorporated odometers into their chariots and carts. These devices typically worked through a geared mechanism connected to a wheel, dropping pebbles, or making a mark after a set distance was covered. In ancient China, during the Han Dynasty, approximately 1st century CE, engineers created their own version of the odometer, often mounted on wagons, complete with a drum-beating figure to signal each measured interval. These instruments allowed for more accurate mapping, road construction, and logistical planning for both military and trade purposes. Today's odometers, whether mechanical or digital, operate on the same principle, measuring wheel rotations to calculate distance. They are an integral feature of virtually every modern vehicle, from bicycles to spacecraft, enabling everything from trip planning to maintenance scheduling. The core concept developed over 2 millennia ago still underpins modern navigation and engineering, showing how a simple mechanical idea from antiquity became an indispensable tool for travel and exploration in the modern world. Number 17. Celestial navigation and star chart navigation for seafaring. Celestial navigation, the art of using the positions of the sun, moon, planets, and stars to determine one's position at sea, emerged in various forms across the ancient world. Early evidence points to the Polynesians mastering star-based navigation as early as 1500 BCE, using memorized star maps, wave patterns, and horizon markers to voyage vast distances across the Pacific. In the Mediterranean, the Phoenicians, approximately 1200 to 800 BCE, became renowned for their use of the North Star, or Polaris, to guide long-distance voyages, enabling trade and exploration far from familiar coastlines. The Greeks further advanced the practice during the Hellenistic period, approximately 3rd century BCE, by creating detailed star charts and celestial globes, while later Roman seafarers relied on similar tools. In the Islamic Golden Age, 8th to 15th century CE, scholars refined astronomical instruments like the astrolabe and quadrant, making celestial navigation more precise and accessible for maritime expansion. Today, celestial navigation still holds relevance, especially as a backup to electronic GPS systems for ships and even aircraft. Modern navigators still use sextants, descendants of ancient tools, to calculate latitude from the sun or stars. Naval academies and survival training programs continue to teach these skills, ensuring that even in an age dominated by satellites, the millennia-old knowledge of reading the skies remains a vital part of human navigation. The stars that once guided Phoenician traders and Polynesian voyagers still light the paths of modern sailors. Number 16. Mapmaking. Mapmaking, or cartography, emerged as a vital skill in the ancient world, allowing civilizations to record, understand, and navigate their surroundings. Some of the earliest known maps date back to around 2300 BCE in Mesopotamia, where Babylonian clay tablets depicted local rivers, fields, and cities. By the 6th century BCE, The Greek philosopher Anaximander is credited with creating one of the first known world maps, incorporating geographical knowledge from explorers and traders. Greek scholars like Ptolemy, in the 2nd century CE, revolutionized cartography by introducing a systematic use of latitude and longitude, creating a framework that would influence mapmaking for over a millennium. In China, detailed maps were being created by at least the 4th century BCE, often with remarkable accuracy for the time. During the Roman Empire, large-scale maps, such as the Tabula Peutingeriana, charted extensive road networks, aiding both military campaigns and trade. Islamic Golden Age scholars from the 9th to 14th centuries synthesized Greek, Roman, Indian, and Chinese geographic knowledge, producing highly detailed maps that guided travelers across continents. The fundamental principles of ancient cartography, including accurate scale, orientation, and representation, continue to guide modern mapmaking, with satellites and digital tools providing enhanced precision. From GPS navigation apps to detailed geological maps, the ancient practice of translating the world into a visual guide continues to shape how we explore, trade, and understand our planet. The world, in a sense, is still drawn upon the foundations laid thousands of years ago. Number 15. Hydraulic engineering. Hydraulic engineering in the ancient world transformed human societies by enabling large-scale water management for agriculture, urban life, and transportation. One of the earliest known examples comes from ancient Mesopotamia around 3000 BCE, where Sumerians built irrigation canals and levees along the Tigris and Euphrates rivers to control flooding and distribute water to farmlands. In ancient Egypt, similar systems along the Nile allowed for the storage and redirection of floodwaters, supporting stable crop production. The Indus Valley Civilization, flourishing between 2600 and 1900 BCE, developed advanced reservoirs and urban drainage systems, while ancient China's Dujianjian irrigation system, built in the 3rd century BCE, remains in use today. In the Mediterranean, the Romans excelled in hydraulic engineering, constructing monumental aqueducts, dams, and reservoirs to supply cities, bathhouses, and farms. They also pioneered the use of waterproof concrete, allowing for more durable water structures. These innovations went beyond mere survival, enabling population growth, urban planning, and economic expansion. Ancient engineers laid the groundwork for channeling, storing, and distributing water, principles that remain in use today with modern materials and technology. Contemporary dams like the Hoover Dam, irrigation canals, and water treatment systems all trace their conceptual lineage to these ancient works. In essence, the mastery of water through hydraulic engineering allowed ancient civilizations to thrive in challenging environments, and its legacy remains a cornerstone of modern infrastructure and resource management worldwide. Number 14. Ink and writing materials. The development of ink and writing materials was one of the most transformative achievements of the ancient world, enabling the recording and preservation of knowledge across generations. The earliest known inks date back to around 2500 BCE in ancient Egypt and China. Egyptian scribes used black ink made from soot mixed with water and gum arabic, writing on papyrus sheets made from the pith of the papyrus plant. In China, early inks were crafted from soot and animal glue, applied with brushes on silk or bamboo slips. By the 2nd century BCE, parchment, that is, treated animal skins, emerged in Pergamon, in present-day Turkey, as a durable alternative to papyrus, particularly valued in regions where papyrus was scarce. The Romans and Greeks adopted both papyrus and parchment, developing colored inks, including red for headings and annotations. India also contributed to the tradition, with early palm leaf manuscripts written using plant-based inks. These innovations revolutionized administration, literature, and science by providing portable, long-lasting means of record-keeping. Inks evolved over centuries, incorporating plant dyes, iron salts, and carbon black, leading to greater permanence and variety. The fundamental principle behind inks remains unchanged, involving pigments or dyes suspended in a fluid and applied to a surface. However, modern inks have advanced significantly through synthetic chemistry, offering improved stability and a wider color range. From ballpoint pens and printer cartridges to archival manuscripts, the ancient marriage of ink and writing surfaces continues to be the foundation of how humanity records, shares, and preserves its ideas. Number 13. Plumbing systems. Ancient plumbing systems represent one of the earliest examples of large-scale engineering aimed at improving public health and daily life. The earliest known examples date back to around 2600 BCE in the Indus Valley Civilization, where cities like Mohenjo-daro featured baked clay pipes for drainage and private bathing areas connected to street sewers. By the 2nd millennium BCE, Minoan Crete had advanced terracotta piping for freshwater delivery, including sophisticated pressure-based systems. The Romans perfected plumbing on an unprecedented scale between the 1st century BCE and the 2nd century CE, constructing aqueducts that transported clean water over vast distances. They employed lead or plumbum pipes, valves, and taps to distribute water to public baths, fountains, and private homes. Although lead's toxicity was unknown at the time, its malleability and durability made it a popular material. Valves, often made from bronze, allowed for flow control, while complex sewage networks carried waste away from densely populated urban centers. These systems drastically improved sanitation, reduced waterborne diseases, and supported urban growth. Modern systems may use materials like copper, PVC, and stainless steel, but the fundamental principles of water distribution and waste removal are still remarkably similar to their ancient counterparts. Today's municipal waterworks, indoor plumbing, and even irrigation infrastructure trace their lineage directly to these ancient innovations. The vision of providing clean, accessible water to all, first realized thousands of years ago, continues to be one of humanity's most vital and enduring engineering goals. Number 12. Cranes. The crane, a pivotal invention in construction history, first appeared in ancient Greece around the late 6th century BCE. Early cranes were human-powered, using tread wheels, winches, and compound pulley systems to lift heavy stones for temples and other monumental structures. Evidence from stone block markings at Greek sites, such as the Temple of Artemis at Ephesus, suggests that cranes replaced older, less efficient methods like ramps, allowing for taller, more complex buildings with greater precision. By the Roman period, 1st century BCE to 4th century CE, cranes had evolved to include multiple pulley systems, larger tread wheels, and even animal power to increase lifting capacity. The Romans used cranes extensively in constructing aqueducts, amphitheaters, and fortifications, with some models capable of lifting loads up to 6 tons. These machines not only sped up construction, but also reduced labor requirements, enabling the rapid expansion of cities and infrastructure. Today's tower cranes, mobile cranes, and gantry systems operate on the same mechanical principles, leveraging pulleys, counterweights, and winches to multiply lifting power, though modern versions use steel frameworks, hydraulics, and electric motors. The fundamental concept devised over 2 millennia ago remains at the heart of modern construction, shipping, and engineering projects. From skyscrapers to shipyards, the crane's ancient origins continue to shape the built environment of the contemporary world, proving that this mechanical marvel was one of humanity's most enduring engineering breakthroughs. Number 11. Gear trains. Complex gear trains, capable of transmitting and modifying motion, reached a remarkable level of sophistication in the ancient world with the creation of devices like the Antikythera mechanism. Discovered in a shipwreck off the coast of Antikythera, Greece, and dated to around 150 to 100 BCE, this intricate bronze machine is believed to have been used for astronomical calculations, including predicting eclipses, tracking planetary positions, and calculating the timing of the ancient Olympic Games. Its internal system of precisely cut interlocking gears demonstrated an understanding of mechanical engineering centuries ahead of its time. Although the origins of gear technology likely trace back earlier, possibly to Hellenistic engineers influenced by Babylonian astronomy, Greek artisans perfected the art of cutting gears with fine teeth to achieve accurate rotational ratios. This innovation allowed for complex movements to be translated into precise, predictable outputs, laying the groundwork for advanced machinery. Today, the principles behind ancient gear trains remain foundational in countless devices. From mechanical clocks and watches to car transmissions, robotics, and industrial machinery, modern engineering still relies on the same fundamental laws of motion transfer that ancient Greek craftsmen mastered. The Antikythera mechanism in particular stands as both a technological wonder and a reminder that sophisticated mechanical computation existed more than a millennium before the development of modern scientific instruments, bridging the ancient and modern worlds through timeless engineering. Number 10. Lighthouses. One of the most iconic feats of ancient engineering was the Pharos of Alexandria, constructed around 280 BCE on the small island of Pharos in Egypt during the reign of Ptolemy II. Standing an estimated 100 to 130 meters tall, it was considered one of the 7 wonders of the ancient world. The lighthouse used an open flame at its summit, amplified by polished bronze mirrors to project light far out to sea, guiding ships safely into the bustling harbor of Alexandria. By day, its gleaming stone exterior and smoke signals provided visual cues for navigation, while at night, the reflected firelight served as a beacon against the dark expanse of the Mediterranean. Although the Pharos was the most famous example, the concept of beacon technology existed in other ancient cultures as well, with signal fires used along coasts and mountaintops in Greece, Rome, and China for navigation and communication. The Pharos, however, elevated this practice into a permanent and monumental maritime aid. Today, the principle behind the Pharos lives on in modern lighthouses, which use high-powered electric lamps and Fresnel lenses to project beams visible for dozens of nautical miles. While GPS and radar have reduced reliance on physical beacons, lighthouses remain critical in certain areas, serving as both safety measures and cultural landmarks. The legacy of the Pharos demonstrates how ancient ingenuity set a standard for maritime navigation that still influences global seafaring today. Number 9. Bookbinding. The Codex, the ancestor of the modern book, emerged during the late 1st century CE in the Roman Empire, revolutionizing how written information was stored and accessed. Before its invention, most texts were recorded on scrolls made of papyrus or parchment, which were cumbersome to handle, required rolling and unrolling, and made locating specific passages slow. The codex format, by contrast, consisted of individual sheets of parchment or vellum stacked, folded, and sewn along one edge, then bound with protective covers. This allowed writing on both sides of the page, significantly reducing material use and making the text more compact and portable. Early adoption of the codex was seen among Roman scholars, lawyers, and Christian communities, the latter valuing its convenience for compiling sacred texts like the Bible. By the 4th century CE, codices had begun to replace scrolls across much of Europe and the Mediterranean. The innovation also opened the door for elaborate bookbinding techniques, including decorated leather covers, gilded lettering, and intricate stitching. Today, the codex format remains the dominant structure for physical books worldwide, from novels to academic textbooks. While digital formats have grown in popularity, the physical codex continues to thrive, prized for its tactile quality, durability, and cultural significance. The ancient shift from scroll to codex not only changed reading habits, but also laid the foundation for the printing revolution over 1,000 years later, shaping the very concept of the book as we know it. Number 8. Abacus. The abacus, one of humanity's earliest calculating devices, dates back to around 2300 BCE in ancient Sumer, with similar versions later appearing in Egypt, Greece, Rome, China, and Japan. Early models consisted of a flat board or table with grooves in which pebbles or beads were moved to represent numbers. The Romans used a portable bronze abacus with sliding beads, while the Chinese developed the suanpan by the 2nd century BCE, a wooden frame with rods and beads that could perform addition, subtraction, multiplication, division, and even square roots. The abacus revolutionized trade, accounting, and taxation in the ancient world, enabling merchants and administrators to carry out complex calculations quickly and without writing down intermediate steps. In societies where literacy was limited and numerical notation cumbersome, it served as a practical and accessible tool. Its design varied across cultures, but its principle remained the same, using physical counters to represent and manipulate numerical values. Today, the abacus still finds use in parts of Asia, Africa, and the Middle East, both as a teaching aid for developing arithmetic skills and as a rapid, electricity-free calculator. Modern adaptations, including virtual abacus apps, preserve its relevance in education and mental math training. This simple yet ingenious invention remains a testament to the ingenuity of ancient problem solvers, bridging a gap between prehistoric counting methods and the digital age's computational technology. Number 7. Algebra. Algebra, as a structured mathematical discipline, began taking shape in the ancient world, with early foundations laid by Babylonian mathematicians around 1800 BCE, who solved linear and quadratic equations using geometric reasoning. However, a significant leap came in the 3rd century CE, through through the work of Diophantus of Alexandria, often called the father of algebra. Living in the Greco-Roman world of Egypt, Diophantus introduced symbolic methods to represent unknown quantities and operations, moving away from purely rhetorical descriptions of problems. His seminal work, Arithmetica, presented solutions to determinate and indeterminate equations, laying the groundwork for future algebraic thinking. Diophantus's methods influenced later Islamic scholars during the golden age of mathematics, notably Al-Khwarizmi, in 9th century Baghdad, whose work systematized algebra and gave the discipline its name. These early algebraic frameworks enabled advancements in astronomy, engineering, architecture, and commerce, where solving for unknown values was essential. Today, algebra remains a cornerstone of mathematics and is applied in countless fields, such as engineering, computer science, economics, data analysis, and even cryptography. Modern symbolic algebra owes much to Diophantus's innovations, as his step toward abstract representation allowed for the manipulation of unknowns without reference to specific quantities. Whether in designing algorithms, predicting financial trends, or programming artificial intelligence, the same fundamental algebraic principles that began in the ancient world continue to underpin problem-solving in the 21st century, making it one of history's most enduring intellectual achievements. Number 6. Planetary Models. The study of planetary models in the ancient world began with the Babylonians around the 2nd millennium BCE, who developed systematic methods to track celestial bodies using detailed observations recorded on clay tablets. By the 7th century BCE, Babylonian astronomers had devised mathematical schemes to predict the positions of planets, eclipses, and lunar cycles, laying the foundation for theoretical astronomy. These models, while geocentric, were remarkably precise for their time and heavily influenced later civilizations. In the 4th century BCE, the Greeks expanded on Babylonian data and introduced geometric reasoning to explain planetary motion. Philosophers such as Eudoxus of Cnidus proposed concentric sphere models, while Claudius Ptolemy in the 2nd century CE created the influential Almagest, which refined the geocentric model using epicycles and deference to account for retrograde motion. Though incorrect in placing Earth at the center, Ptolemy's model remained the dominant astronomical system for over 1,000 years. These early planetary models were vital for navigation, agricultural planning, and religious calendars. They also formed the intellectual stepping stone toward the heliocentric revolution of Copernicus in the 16th century. Today, the principles of careful observation, predictive modeling, and mathematical representation, pioneered by the Babylonians and Greeks, remain central to modern astronomy. Space missions, orbital mechanics, and astrophysics all rely on mathematical models of planetary motion, an enduring legacy of ancient curiosity and ingenuity about the heavens. Number 5. Distillation. Distillation, the process of separating substances based on differences in boiling points, has its origins in the Hellenistic period, around the 1st century CE, in the city of Alexandria, Egypt. This era, a melting pot of Greek, Egyptian, and Middle Eastern knowledge, saw the rise of early alchemists such as Maria the Jewess, credited with designing some of the first distillation apparatus, including a 3-armed still known as the trabecos and the keratakis, used to heat and condense vapors. These devices allowed for the purification of liquids, the extraction of essential oils, and the production of medicinal substances. Initially, distillation was primarily employed for creating perfumes, preparing herbal extracts, and experimenting with alchemical transformations. Over time, the technique spread to the Islamic world, where scholars such as Jabir bin Hayyan, 8th century CE, refined the method, making it more efficient and expanding its applications to include the distillation of alcohol and chemical solutions. Today, distillation remains a cornerstone of modern industry and science. It is used in the production of beverages, fuels, pharmaceuticals, and purified water. The basic principle developed in ancient Alexandria, which involved heating a liquid to produce vapor, then cooling it to collect the purified substance, remains unchanged, though the equipment has evolved dramatically. From ancient glass stills to industrial-scale columns, distillation stands as one of the most enduring chemical processes, a testament to the ingenuity of Hellenistic alchemists and their lasting impact on technology. Number 4. Dyeing techniques. Ancient dyeing techniques were both an art and a science, developed over millennia to produce vivid, lasting colors from natural sources. One of the most famous was Tyrian purple, derived from the secretions of the murex sea snail, perfected by the Phoenicians around the 15th century BCE in the eastern Mediterranean. Producing just a small amount of this dye required thousands of snails, making it more valuable than gold and a symbol of royal and imperial power. In India, as early as 2000 BCE, indigo dye was extracted from the Indigofera tinctoria plant, becoming one of the most traded and sought-after colors in the ancient world. Meanwhile, in regions such as Egypt and the Middle East, madder root was cultivated to produce rich reds and oranges, with evidence of its use dating back to at least 1500 BCE. These dyes were applied to textiles through complex processes involving mordants, which are chemical agents that fix the color to the fabric, ensuring the hues remain vibrant over time. The knowledge spread across civilizations, influencing clothing, trade networks, and cultural identity. Today, while synthetic dyes dominate textile production, natural dyeing methods inspired by these ancient techniques have seen a revival, especially in sustainable and artisanal fashion. Tyrian purple, indigo, and madder are still produced using traditional processes by craftspeople, preserving the legacy of ancient chemists and dyers. Their work laid the foundation for modern color chemistry and the global textile industry. Number 3. Bridges. Ancient bridge building was a transformative achievement that expanded trade, communication, and military movement across difficult terrains. Early examples date back to Mesopotamia around 2000 BCE, where simple wooden or stone slab bridges spanned small rivers and canals. The ancient Chinese also developed sophisticated timber beam bridges by the Zhou dynasty, some incorporating early suspension techniques using ropes and chains. However, it was the Romans, from the 3rd century BCE onward, who elevated bridge construction to an unparalleled level of engineering mastery. Roman engineers perfected the use of arches in stone bridges, allowing them to span greater distances and support heavier loads. They employed durable materials like volcanic pozzolanic concrete and precisely cut stone, creating structures such as the Pont du Gard in France and the Alcantara Bridge in Spain, both still standing after nearly 2 millennia. Many Roman bridges featured roadways wide enough for chariots and were integrated into the empire's vast road network, enabling rapid troop deployment and efficient commerce. Today, the principles of ancient bridge building remain foundational in modern civil engineering. The use of arches for distributing weight, durable construction materials, and careful site selection are all techniques inherited from antiquity. While contemporary bridges use steel, reinforced concrete, and advanced suspension systems, their design owes much to the ingenuity of ancient builders. Many modern engineers still study Roman and Chinese bridge construction for insights into durability, sustainability, and aesthetic harmony, proof that the ancient art of bridging distances continues to connect our world. Number 2. Acupuncture. Acupuncture is an ancient healing practice that originated in China over 2,000 years ago, with roots tracing back to at least the Han Dynasty. References to the technique appear in the Huangdi Neijing, which means the Yellow Emperor's Inner Canon, one of the oldest surviving medical texts. In its earliest form, acupuncture involved the insertion of fine needles, originally made from stone, bone, or bronze, into specific points on the body to regulate the flow of qi, the vital energy believed to travel through channels known as meridians. Practitioners aim to restore balance between the body's opposing forces, yin and yang, thereby promoting natural healing and preventing illness. By the Tang Dynasty, 618 to 907 CE, acupuncture had developed into a highly systematized discipline with detailed charts mapping hundreds of acupoints. It spread to Korea, Japan, and eventually the Islamic world, ensured it became a cornerstone of traditional medicine in Asia. In the modern world, acupuncture is widely practiced both as a traditional therapy and as a complementary medical treatment. While modern science often frames its benefits in terms of nerve stimulation, endorphin release, and improved blood circulation, many practitioners still follow the classical meridian theory. Today, acupuncture is used to relieve pain, reduce stress, aid digestion, improve sleep, and treat a variety of chronic conditions. Its integration into hospitals, wellness centers, and alternative health clinics worldwide demonstrates how a healing art born in ancient China continues to play a vital role in global healthcare. Number 1. Medicine. Ancient Egyptian medicine, one of the earliest structured medical systems in history, flourished as early as the Old Kingdom period, approximately 2686 to 2181 BCE. Figures like Imhotep, the polymath architect and physician of the 27th century BCE, are often credited as pioneers in this field. Egyptian medicine combined practical treatments with spiritual beliefs, reflecting their view that health was influenced by both physical and supernatural forces. The Egyptians developed detailed medical papyri, such as the Ebers Papyrus, approximately 1550 BCE, and the Edwin Smith Papyrus, approximately 1600 BCE, which recorded diagnoses, surgical procedures, and herbal remedies. These texts reveal knowledge of anatomy, wound care, bone setting, and even dental treatments. The Egyptians employed a range of tools and techniques, including suturing wounds with linen, using honey as an antiseptic, and performing basic surgeries. Herbal medicine played a major role, with ingredients like garlic, aloe, and myrrh prescribed for various ailments. While religious rituals and incantations often accompanied treatments, many of their methods were remarkably effective by modern standards. Today, the legacy of ancient Egyptian medicine survives in both the scientific and holistic approaches to healthcare. Practices such as herbal remedies, wound sterilization, and structured medical documentation echo through modern medicine. Furthermore, the integration of physical treatment with attention to mental and spiritual well-being, a hallmark of Egyptian healthcare, remains a guiding principle in many medical systems around the world. And there you have it, the top 46 ancient inventions that shaped the world we live in today. From the ingenious wheel to the life-saving practices of ancient medicine, these breakthroughs prove that human creativity knows no bounds, even across millennia. Which invention surprised you the most? Let us know in the comments below. If you loved diving into the brilliance of our ancestors, don't forget to like this video, hit that subscribe button for Ancient Odyssey, and ring the bell so you never miss a journey into the past. Share your thoughts, and let's keep exploring the wonders of history together. See you in the next video.